Hey, good morning, afternoon, or evening, everybody. Welcome to the Don't Pass the Salt. NASA's Salinity mission continues with SMAP webinar, and this is your host, Jennifer Brennan. So while everybody's logging in here, you've probably already noticed that we have two optional polls, and you'll find those located at the bottom left and middle portion of your page. And I would like to thank all of you in advance for your feedback on these polls. It's 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started. And what I usually do first is just go over a few logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you should see that located on the lower right-hand corner of your screen. This works like a chat. We are recording today's webinar. The recording will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a few days of completion. And what I'll do is I'll send an email to all registrants with links to the two recordings. In addition, today's presentation files, including the data animations or the movie files, will be available for download at the end of the webinar. Regarding timing, today's webinar is a bit longer than our usual NASA Earth Data webinars. The presentations and live demonstrations will comprise the first hour, and then we've allocated an additional optional 30 minutes for the question and answer period. So once all of our speakers have finished with their presentations today, what we'll do then is we'll transition to an optional final set of polling questions. And then from there, we'll move directly to the Q&A period. All right, at this point, I'm going to pull up today's agenda. During today's webinar, we do have 3 speakers. Our first speaker, make sure that's pulling up here. Okay, great. Our first speaker, Dr. Tomas Meisner, is a senior research scientist at Remote Sensing Systems and will provide an introduction to sea surface salinity data. And then next, our second speaker, Dr. Vardis Santos, who is the lead data engineer for the Aquarius mission at NASA's Physical Oceanography Distributed Active Archive Center, or PO.DAAC, will discuss some of the key data discovery and access mechanisms that are available to you. And during this part of the webinar, he will actually include a step-by-step live demonstration. And then finally, we will wrap up today's webinar with our third and final speaker, Dr. Jorge Vasquez, who is a sea surface temperature and salinity research scientist at NASA PO.DAAC. And he will present a use case that looks at the Gulf of Mexico, looks at the sea surface salinity data, I should say, within the Gulf of Mexico. And he will also provide this use case through the live access server, which is a tool or application that's available through PO.DAAC. With that, it is my pleasure to introduce today's first speaker, Dr. Tomas Meisner. Dr. Meisner?
Very good. Okay, so I'm ready to start, I guess.
Fine.
So I'm talking about the basics of NASA salinity, or I should say more precisely the basics of the measurements of salinity with NASA instruments. So Jennifer, if you could please advance the slide. Yeah, thank you. So salinity, as you know, is a measurement of the weight or the concentration of dissolved salt in the ocean, in the seawater. The salts we are talking about are, of course, mainly sodium chloride, but as you can see from the chart here at the bottom, there are a number of other constituents as well. There are some calcium, potassium, magnesium, and some sulfate also, and so some other minor constituents. But it's mainly sodium chloride, which is dissolved in the ocean water. The basic measurement is a unit weight ratio. So we basically measure the weight of the salinity, the dissolved salt, per 1,000 gram or per kilogram of water. And that is expressed in general as a dimensional unit called practical salinity unit, PSU. And the average of it is about 35. over the world ocean. That means on average we have about 35 grams per 1,000 grams of seawater concentration in the ocean. So that's basically what we mean when we say the salinity is 35 PSU. If you could advance a slide again, please, Jennifer. Yeah. So a little historical background, how has been salinity measured originally or historically. Ships have taken seawater in and have measured salinity. I figured out that salinity is higher than average in areas, in gyres and in areas where we have lots of evaporation. For example, the Mediterranean Sea. We'll see a couple more examples in a minute. And low salinity is, of course, where you have fresh water intake that happens where it rains a lot in the tropics, also near big rivers, and at high latitudes where the sea ice is melting. With big rivers, I mean the really big outflows of the major rivers like the Amazon, the Congo River, Gulf of Bengal, and so on. They discharge into the ocean, and those regions the salinity is low. It means the water is fresh. Since about the year 2000, there has been a scientific network, which is a international collaboration, as a matter of fact. It's called Argo, and there are profilers. They are basically drifting floats, which go up and down from the sea surface down to below the surface, and they measure the salinity electronically. We'll talk about it in a minute. So if Jennifer, you could please advance the next slide. Yeah. So we're showing in a minute a little movie about the salinity change over the ocean. As I had mentioned, 35 PSU is which means 35 per 1,000 gram per 1,000 gram seawater is the average. And on that color scale that you see on this slide, it's 35 is a green, so that's sort of the average value. But then there are areas where the salinity is lower, and it's blue, and where the salinity is higher, which is red. So there is a salty water, and then the fresh water is blue. And the scale over which that happens over the world ocean roughly goes from 30 to 40. So 35 is the average, plus minus 5. It's basically what happens. We're now going to show a little animation which displays the salinity from the first NASA satellite that has measured salinity. And Jennifer just started it. I think we're going through it twice. So if you look at the movie, you see, or the animation, you see the freshwater outflow. I'm pointing here with my arrow. That's the Amazon here. You see how it goes out. Also here in the Gulf of Bengal, there's another area where they actually have a really low salinity. And then you see the melting and the freezing, the poles changing. And on the other hand, like here, that area I'm pointing right now, that's in the northern central Atlantic subtropical region. That's a region where we have very high salinity, or relatively high salinity, going up about 38 PSU, and that's largely caused by evaporation. Another region here is the Mediterranean, which I'm pointing to right now. It's here at the edge, the very left edge. It's another area with relatively high evaporation. In other words, the salinity is largely a proxy for the global water cycle. It characterizes evaporation, precipitation. It's another region which I should point to here in the intertropical convergence zone. I'm going up with my arrow here. That's again when you have high precipitation, the salinity gets low. And then also river outflows. So you have the Amazon again here. Here is the Congo River. That's over here in Africa, another region. And then Gulf of Bengal, which is actually both. It has high rain and it has also big river outflows. Okay, yeah, so we are done with the movie. We can, I think, try to switch back to the slides now. So again, that was from the Aquarius measurement. Now talking a little bit about how do we measure salinity, or what's the whole idea about measuring it. Salinity changes, the concentration changes the electric or the dielectric properties of seawater. It's basically the response of the water to an electric field. And that itself changes also the emission. And the emission, the microwave emission, the radiation which is emitted by the seawater, that's what a satellite like Aquarius measures. And we measure it basically just from the very top, about 1 centimeter of the ocean surface. And what that chart here shows is emission, which we call brightest temperature. It's basically a proxy for the power that is of the electromagnetic radiation that is emitted from the sea surface as a function of salinity. And then we show that for 4 different temperatures, which is, so I'm pointing here, the black line is a very cold temperature, 0 centigrades, and then we go up to high temperature, 30 centigrades. And we have, in those instruments, we are having 2 channels that measure 2 polarization. There's a horizontal polarization, a vertical polarization that helps with the measurement. I'm not going to get into details, but what you see from the chart is, when you look at those red curves, so the high temperature, you get a pretty good signal. So I mean, the brightness temperature or the power of the electromagnetic radiation decreases pretty clearly over the range of salinity from 0 to 40. That's for both of the channels. And then if you go from the red to the black, going from high temperature to low temperature, you see at low temperature there's very little change. That means at cold water, at low temperature, we have very little sensitivity of our measurement to salinity. It means we need to expect high errors because of that. So in other words, to make it brief, at high temperature, warm water, we can measure salinity better than we can do it at very cold water. So the errors we are producing in cold water are much larger. That is something to keep in mind. Yeah, so we could maybe take the next slide, please. Okay, so now what I'm going to show now is, as I just mentioned, we're measuring basically the emission, electromagnetic microwave emission, thermal microwave emission from the ocean. Assuming we have a flat surface, then we can easily get salinity. The sensor, that means it's what the satellite sensor, the receiver, is measuring. So that is that yellow arrow, which shows basically the signal we are interested in. Unfortunately, there are a lot of other sources from the sky, from the earth, which disturbs that measurement, and we are going through them now sort of step by step, so that you can see what else is happening. So next slide, please. The first thing is the sun. The sun can enter the sensor directly. It's a generally very small part, but then it can also go down to the ocean and get reflected, or it can even get backscattered from the ocean surface. So that creates an error source, and something similar is happening with the moon. The moon is much, the radiation from the moon is much smaller, so it's not that big of a problem, but the sun is a big issue in that measurement. So next slide, please. Next to the sun, there's also the galaxy, Milky Way, and then there's a cosmic microwave background, 2.7 Kelvin from the Big Bang, which is radiating, and that also enters the sensor either directly or it can again get reflected, and it's again actually a pretty big error source that we are having to deal with. So next one, please. And then the radiation from the ocean, in order to get to the sensor, it has to pass through the atmosphere. It gets absorbed, and also again the atmosphere itself can radiate, and that creates a spurious error source. And then above the atmosphere we have the ionosphere, and the ionosphere mixes up those two polarizations which I mentioned earlier, the vertical and the horizontal polarization, and that's again an error source we have unfortunately to deal with. And then the next slide, please. Now we're going down to the ocean surface. The ocean surface is not flat, but it's rough. The wind which is blowing over the ocean is roughening it. It creates ripples, it creates foam, and that foam disturbs the signal, and both of them actually disturb the signal as well. And that's actually the largest error source we have, so the roughness due to wind over the ocean, which we need to deal with. And then finally, next slide, Jennifer, please. Finally, there's also radiation from land. If you get close to the coast, in particular, like those river outflows we've been talking about, there's stray radiation from the land, which enters the antenna from the land surface, and that's another error source. And to make it worse, there's also human-created error sources, which we call RFI, radio frequency interference, that is from like aircraft radar and things like that, cell phones, towers, and all kinds of things which are human-created. If it's near the coast, then it can influence the ocean measurement. It sort of contaminates it. And there are basically all of our error sources we have. Now what we need to do in order to measure salinity accurately, we need to take all of those error sources, and that's basically the job of the salinity retrieval algorithm that NASA has implemented from the sensor, NASA sensor, and then we basically systematically take all out of the error sources as much as we can to be able to come to a salinity value. Next slide, please. I mentioned Aquarius. That was the first NASA instrument that measured salinity. There had been, it's actually still working in a European instrument called SMOS, which was the very first instrument that measured salinity. The Aquarius, the NASA instrument, was launched in 2011, June 2011, and it provided salinity for almost 4 years, till about 2015, when there was actually a failure on the power in the satellite, the power transfer. So about almost 4 years we have measurements from NASA. It was a combined, a joint mission between NASA, US, and the Argentinian Space Agency. I need to mention that. The requirement for the Aquarius is when we take the salinity, average it over monthly time scales. We have seen in the movie that the salinity is changing relatively slowly over time scales. It's about 150 kilometers. And about 150 kilometer averaging, and over monthly averages, then we need to have it 0.2 PSU error is allowed at maximum. Again, the average value is about 35 PSU. It's a pretty strict accuracy requirement, and we were able to meet that with our measurement. The latest Aquarius version 5, which is a final mission reprocessed version, which is available at NASA, actually was able to reach it to about 0.13 PSU. So we were a little better, in other words. Next slide, please. What that slide shows is how the instrument is assembled. So lots of electronic, complicated electronic, which you see the people assembling here. It's extremely stable, which is a very costly design, because we need to be able to measure high accuracy 0.2 PSU requires that we can measure the brightness temperature at about 1/10 of a Kelvin. It's a really, really accurate, very accurate requirement. We had Aquarius had a radar, or what's called scatterometer on board, which was able to measure the roughness of the ocean. So that helped to get rid of one of those signals that I mentioned earlier. It was good. It avoided the sun. It was put in an orbit so that the sun intrusion is minimal, and it provided global coverage and repeated sampling with about 7 days repeat cycle. So next slide, please. That again shows the Aquarius, how it flies in orbit, and in a minute we're showing a movie. I just want to point here to the what we call the beams. It had 3 beams. Aquarius had 3 beams, and they were fixed. It didn't rotate. It didn't change. It was just going along with the instrument. It was at 3 various incidence angles from 26 to 40 degrees, and it was cutting out a swath of about 390 kilometers in total. That's a relatively narrow swath. All those instruments, the Aquarius and the next instrument I'm mentioning, they all work at the lowest, or very low microwave frequency, which is the L band. It's about 1.4 gigahertz. And then I think we are ready to look at the Aquarius in orbit. If you can start the movie, please. Yep. I think it's going to take a little while till it loads. So that's the Aquarius here. Yeah. You see here that dish is the antenna. On the left side is the solar panel. And now it takes observations, and that's its swath it's cutting out. So that colors we have out the salinity over the ocean. And it has just it crosses a pole from north to south, south to north, and then at each crossing it shifts a little bit, and that's because the Earth is turning and cutting out a swath. Here it's coming now north from the South Pole. It's cutting out another swath, which is a little bit shifted westward. The orbit is always the same. The Earth is turning. That's why you can sort of cutting out those swaths, and that's after about a week of data or a week of measurements. We basically have filled up the whole Earth with salinity, and that's what the movie has been showing. Yeah, that's sort of the idea how the measurement is progressing. Next slide, maybe. Now I'm coming to the second instrument. As I mentioned, Aquarius failed. It was in 2015. Fortunately, in early 2015, there was another instrument launched called SMAP. It stands for Soil Moisture Active Passive. It was designed originally to measure soil moisture, as the name suggests, but it can also measure salinity. It's L-band microwave spectrum, same as Aquarius. Has a little bit different features. The basic radiometer design, receivers and so on, are very similar than Aquarius. It has an antenna, so that big dish, which is a little bit emissive, so it is emitting radiation rather than just reflecting it, and that creates an erroneous signal, and that erroneous signal gets pretty large when the spacecraft is eclipsed by the Earth, when it's sort of shielded by the Earth from the sun, because then you get a really big swing in the temperature, and that creates a little problem, so we have to take it out. But I think we are ready to show the movie now. So that shows the SMAP now. It's much larger than Aquarius. As you can, as the movie actually suggests. So again, we have here, down here, the solar panels, and now we're going spinning. We see a spinning antenna now, a really big antenna, so that is that dish. It's made up out of mesh in order to save weight. And it's about 6 meters in diameter, so it's a really large antenna, and it's spinning around. So that's a basic SMAP. I think we show it again, I guess. Yep. So again, here's the solar panels, left and right. And then you see there's a rotating assembly. And other than the Aquarius, which was just looking into one spot, it's spinning around. Here's the big antenna rotating around, and it cuts out a big circle on the Earth's surface, which gives us really good coverage for this map. Yeah, I think we can swap back to the main slides here. So again, that shows it sort of a little schematically. SMAP instrument, it spins at about 15 revolvings per minute, or 1 revolution every 4 seconds. It's what the figure shows here, sets a satellite here as it spins up here, and then sets a track it cuts out when it flies along. And because of the spinning, you're getting that circle cutting out. You get a really large swath, about 1,000 kilometers, compared with the Aquarius, which was only 390 kilometers. So we have a much bigger coverage, so we're getting much more data. So that is an advantage of the new SMAP instrument. Next slide, please. Here you see here down by the way, that is the circle it's cutting out. That's just a brief comparison between Aquarius and SMAP. They're about the same altitude. Repeat time of the orbit is also pretty close, 7 versus 8 days. They both observe the Earth at 6 p.m. in the ascending orbit and 6 a.m. corresponding in the descending orbit, both of them. The antenna, again, much larger in SMAP, and it's spinning. And because of that, we get a much larger coverage, wider swath. And in 3 days, we already have covered basically the whole Earth. In Aquarius, we had to wait for 7 days. The footprint size, that's the spatial resolution, is large in Aquarius, so it has a relatively low spatial resolution compared with SMAP. 150 Aquarius were about 40 kilometers with SMAP. And the operation period from August to June 2015 for Aquarius, the SMAP is still in orbit. Another little difference I should mention is the Aquarius has a scalerometer or that radar which measures the roughness, and therefore very accurately, as a matter of fact, a very good accurate measurement of the roughness. SMAP had a radar too, but it failed after a couple months in orbit, and in order to do that roughness correction, to get rid of the spurious signal, we need to bring in external wind sources. That is a little bit of a difference, or a little bit of a disadvantage of SMAP. If it had a radar, it would certainly help more to do that correction. Again, as mentioned down here at the bottom as a footnote, SMAP has a small footprint, 40 kilometers, so you can reach a higher spatial resolution. As a trade-off, however, as you know, there's a trade-off between resolution and noise. SMAP is much noisier than Aquarius, so one has to keep that in mind. We are doing, for the product we are giving out, and Dr. Vasquez and Dr. Saunders will mention that later, we are having average of this map to higher footprint sizes. As a matter of fact, we go to about 60 or 70 kilometers. And I think that we have one more slide, I guess. Yeah, that's my final slide. So SMAP are processed, there are different algorithms which NASA has commissioned to produce SMAP data. One is by our institute, Remote Sensing Systems, and then our colleagues from JPL also have an algorithm. The data are available at PO.DAAC. We have orbital data, level 2, what we call level 2 data, mapped on the swath. And then we also have gridded global maps, level 3 data. And we produce those maps for 8-day average, which was a repeat time for SMAP. And we also produce them for monthly averages. So there are maps every month and every week, in other words. And sampling, as I just mentioned, we have 40 kilometers, the original resolution, relatively noisy data. We go to higher footprint, so worse resolution. but still pretty good compared with Aquarius, which is 150 kilometers. We go into 70, or the colleagues of GPL 60 kilometers to cut the noise down. And that is basically all I have to say. So I thank you very much for your attention.
Okay, thank you very much, Dr. Meisner. At this point, what we'll do is we will turn it over to Dr. Vardis Santos, who will discuss sea surface salinity data discovery and access tools. Vardis?
Thank you, Jennifer, and also Tomas for a very interesting presentation. In this part of the webinar, I'm going to be describing some ways that users, the science community, can discover and access NASA salinity data from the PO.DAAC. I have some initial slides, and then some of these concepts will be reinforced with a live demonstration of some of the tools and capabilities. Okay, just so that you are aware, all the NASA salinity data, the official repository for those is the PO.DAAC, which stands for Physical Oceanographic Data Active Archive Center, located at JPL, Jet Propulsion Laboratory in Pasadena, California. Okay, and so all the NASA salinity data are archived here. That includes not only the SMAP and Aquarius data that Tomas was describing, but also some select NASA field campaign data relating to salinity. So we also have some in situ observations as well that relate to these satellite missions. Okay, so in addition to the salinity data, NASA also hosts a variety of other physical oceanographic data sets relating to sea surface temperature, ocean surface winds, altimetry, and gravity as well, just so that you are aware. And not only do we archive these data sets permanently here, but we also provide a variety of tools and services for searching for these data, discovering them, and then accessing, extracting, subsetting these data sets, and doing some basic visualizations and even some basic analyses on these data. So I'll be describing some of those capabilities today in the context of salinity. Okay, the primary mechanism really to access our data holdings is via the PO.DAAC portal, and at the top we have a little menu bar, as you can see in the PO.DAAC portal. If you click on the missions tab, okay, there's a variety of tabs, but if you click on the missions tab, then we highlight here the salinity-related satellite missions, SMAP and Aquarius, and you just click on one of those buttons to take you to the corresponding mission page. And the mission page is just a single sort of point of entry to some of these mission data sets. In the main panel, there's a description of the mission. In this particular case, we're looking at the SMAP salinity mission page, some illustrations of what the data looked like when mapped and output. But really, I think for a lot of users, beyond that introductory information, the key part is on the right-hand panel, and in particular, you'll see that there's different portions of it. There's a series of links to the data. There's a series of links to tools and services through which one can access these SMAP salinity data in this case. And significantly, there's also a panel relating to the technical documentation. So things like the algorithm theoretical basis document, data format guides for the data products, users guides that PO.DAAC may have developed. All of those are accessible via those links through this mission page. Okay, and so if you do click, for example, one of the data links, in this case, browse SMAP salinity data at PO.DAAC, what happens is an automated search happens of our catalog entries, and it returns a series of data set listings that match the given keyword. In this particular case, it's SMAP. And on the panel on the left, there are some filters that can be applied to limit the entries that you see to types of data maybe of particular interest to you. For example, you can filter out by product level, level 2 versus level 3, by resolution, by time period, by latency, etc., etc. So this is what they call faceted search that allows you to condition what you actually, the catalog entries that are returned via the search interface. Okay, and if you click on one of those links to these data sets, you will basically get more detailed information. The types of data for SMAP that we have, or SMAP salinity related that we have at the PO.DAAC, Dr. Meissner already described. We have level 2 orbital data, and we have products both from RSS, the 40 kilometer natively sampled version 2 data of the RSS SMAP salinity data, and also a version of the data set that allows feature resolution at 70 kilometers, again for version 2 of the RSS data. In addition, we, as Dr. Meissner described, we also have this PI-provided SMAP salinity data from JPL, which is at 60 kilometer feature resolution. So those are the 3 level 2 products that we currently have. I just want to point out that RSS is working on a version 3 of its SMAP salinity data products, and that should be out later this fall. Okay, so in addition to the orbital or swath level 2 data, we also have level 3 gridded products, and we have an 8-day running mean daily product. Again, both from SMAP, from RSS for the 40 kilometer and 70 kilometer resamplings, and also from JPL via their retrieval algorithm. And we also have corresponding monthly products. So these are the data aggregated on a monthly time scale. Again, for those feature resolution resampling levels. 2 from RSS, and again 1 from SMAP. Okay, and at this time we can transition over to the live demonstration, which will be via my web browser. And if you click on that, okay, so that's the easiest way of getting to the PO.DAAC web portal. And as I said before, if you click on missions, you will see Aquarius, SMAP, and SPURS as the salinity-related missions for which data we have here. So let me click on SMAP. Again, the central portion has general information on the mission, a little animation, and some imagery. And then, as I said before, the important parts probably for a lot of users is the series of links to technical documentation and to the data. Now, in the slide presentation, we showed how you can essentially just click on this browse SMAP salinity data link to get to all the SMAP data. However, just to point out that you could also just, in this little search toolbar, you can type SMAP, and you'll get the equivalent search results. And as you can see, you get a total listing of 9 matching data sets, and the panel on the right where you can filter these down. So just to point out as well, you have some brief descriptions here, but if you click on the specific links themselves, you will get much more information. I just want to point out that it's being hidden, unfortunately. Okay, there is a different way of viewing these. If you have long listings of data sets, you can change the view mode so that you get this more tabular kind of listing. And from this, let me just select one of the 8-day running mean 70 kilometer SMAP RSS product. And now this gets you into and provides much more detailed information about the data set. There's a description. There's information about the spatial extent, the temporal resolution, the latency, the time period of coverage. Okay, so general information that's useful in terms of deciding on to select for a given data set. Okay, and there's a variety of other tabs as well. If you click on the documentation, there's a series of links here. Probably of most use is the user guide documentation, but we also have links to external websites that have relevant information related to this data set. The citation tabs essentially says how you should cite this data set in any papers that you write. There's pointed to the DOI entry as well. And the granular listing essentially just provides a very quick method of looking at what data files, in fact, are available. Now, this is not the best method of accessing the data themselves is via this data access tab, and you can see there's a series of sections here. The primary mechanisms of accessing the data are under this direct access area. In addition to FTP that everyone is familiar with, we provide access to the data via a range of web services such as OpenDAAC and Threads that additionally provide you with the capability of potentially subsetting the data set for a given spatial and temporal domain of interest. Okay? And then we have, where they exist, there are pointers to applicable visualization and other kinds of tools and services that we have available for a given data set, and then pointers to reader software in a range of scientific computing languages that users can leverage in order to start working with the given data. So everyone is familiar with FTP, but what I want to demonstrate in this particular webinar is how to access the data in a manner equivalent to FTP via this new capability called PO.DAAC Drive. Essentially, FTP at NASA in future will be deprecated for security reasons, and so access to all NASA datasets at all DAACs will be via HTTPS protocol. And the PO.DAAC Drive utility at PO.DAAC allows one to essentially access the data in a very comparable manner to FTP, but just via this more secure HTTPS protocol. So let me just click on that. And essentially, there is actually a kind of a user login screen generally before you actually get to the screen that you're currently looking at. It requires user registration with NASA ESDIS, but it's a very straightforward process, and PO.DAAC can provide further information if there are any questions subsequently on this. But essentially, as with any FTP client, you essentially get a view of the various directories for that given product, in this case the 8-day running mean product, and you can drill into any of those directories and potentially then click on a data file or granule to download that product. So it's the nice thing also about this HTTPS access and this PO.DAAC Drive utility is that in fact you can, using this WebDAV capability here, you can map this drive as a network drive onto your computer, and additionally you can script the downloading, automated downloading of data files via the HTTPS protocols. We at PO.DAAC maintain an active forum, and if you in fact go to the forum, which is available from the main menu, you click on forum. If you just type in Drive in the search bar, okay, and you scroll down a bit, you will see some data recipes relating to PO.DAAC Drive. And so these data recipes allow you to become more familiar with the Drive tool and how you would actually implement scripting to automate downloading of data if that's of interest to you. Okay, let me go back, and as the next part of the demonstration, I'm going to show you how you can access also the data, subsets of data in space and time via Threads, via the Threads server capability. Threads is a widely used server for serving out Earth science data sets, and it packages together a range of data access mechanisms, including OpenDAAC, that some of you may be familiar with, WCS, which is a coverage service, WMS, which is essentially a mapping service for getting visual data layers. But what I want to show you today is this NCCS subsetting service. So let me just click on that for the given data set. Again, we're dealing with the 8-day running mean 70-kilometer product. This is a very simple sort of web interface form where you just click what variables you're interested in subsetting. These are all the variables in this particular data product. You can then select a spatial area of interest for subsetting. So let me just pick a small area so that this is quicker. And okay. And let me also just pick a very a relatively short time period. Now, you may have noticed that as I was typing in and making these selections, this gray portion here with this very large URL was actually actively being constructed. So this is very helpful because by studying a little bit the structure of this URL, you can then learn how to, in fact, implement threads calls via scripting routines that you may write, essentially just substituting your latitude and longitude coordinates and also time intervals. So let me just click the button. This may take a second. That was relatively quick, but essentially it already did the subsetting operation, and you can then save the file to your computer where you can analyze it in any scientific software of your choice, such as MATLAB, IDL, etc. So very straightforward, very powerful, and very useful. Okay, so that is the threads subsetting service. Oops, excuse me. And as a final part of my demonstration, I'm just going to show you a tool called LAS, Live Access Server, that we have at PO.DAAC, that allows you to do some basic imaging and even some basic analysis of data, visual analyses of data. So the first step is really just to select your data product, and you can see that essentially we have a whole range of data sets available here in LAS from PO.DAAC Data Holdings, including Aquarius products, some SST. Let me scroll further down, and again, for consistency, let me pick again the SMAP level 3 70-kilometer product. You select a variable, okay, and immediately it goes in, and actually on the back end it is using the thread service to undertake a subsetting operation on the data files in the collection to produce an output image. Now, this is at the very beginning of the time series, but let me pick for a later period. And the tricky thing to remember always is that unless you check this little box in the top left-hand corner next to the update plot button, you will manually need to press the update plot button itself every time you want to change a selection. So now that I've done that, automatically it has refreshed, and I can go around and select data, say for the next month, same day, and it does the temporal subsetting and the visual display. Now, you can also use this little widget, this little map widget, to define a smaller area. This is the global data set, but say you're interested in the sort of Eastern Tropical Pacific region, you can draw a box. And again, for that same time period, it goes ahead, conducts the back-end subsetting operation, and presents the data for that time period. And you can step in time on a daily basis as you need. Now, LAS also supports a range of other types of plots, which I won't go into today because of time reasons. But essentially, you can do time series plots at a given location, or Hofmuller plots, which are zonal plots over time, and which are very useful. So already this visualization tool is quite helpful for analysis purposes. The final thing that I want to demonstrate with LAS is that, in fact, you can use this tool to subset and extract the data, download these these data to your computer. So if you click the Save As button on the top right here, it brings you up a little interface. You can, for the selected region, okay, that I picked for that Eastern Tropical Pacific area, okay, it will do a subsetting operation and output the file to a given format, and several are supported, so say NetCDF or ASCII if you prefer. And then again, you just select a time period of interest, you click the Save button, and again, it goes on and very quickly does the subsetting operation. What it returns is an aggregate data file with all the 8-day running mean data over this 1-month time period for that geographic location that we selected. And that is all in terms of my demonstration. My colleague, Dr. Jorge Vasquez, will be describing more how LAS can be used for looking at data for science purposes in his presentation now. Thank you.
Okay, thank you, Vardis. Let's transition to our Gulf of Mexico use case with our third and final speaker for today, Dr. Jorge Vasquez. Dr. Vasquez?
Thank you, Jennifer. One of the questions working at the PO.DAAC that we get a lot is, what data set do I use? And you've already seen that there are several salinity data sets, you know, that are available for research and applications. So we wanted to present a specific example using the live access server that Dr. Santos just mentioned, and a specific example basically using the Gulf of Mexico. Nothing inherently special about the Gulf of Mexico, but it is a semi-enclosed basin that has a lot of salinity variability because of river discharge and also evaporation and also the loop current that comes in from the Atlantic and the Caribbean. So it's a highly variable area of salinity, and we're going to use it as an example, you know, using LAS in terms of some of the functionality that you can use to compare these different salinity data sets. Next. Thank you, Jennifer. So in terms of, you know, some of the specific things, plotting SMAP data and LAS, we'll show you a little bit of a, again, an example using the tool and some of the things that you can do, you know, in terms of time series analysis. And we're also going to focus, again, just for the sake of this example, on two of the salinity data sets, the remote sensing 40-kilometer data set, the 8-day running mean, and the remote sensing system 70-kilometer 8-day running mean. These are both project, you know, mission data sets. And we're going to just focus on these two data sets for the sake of showing the functionality of the live access server, but there's nothing inherently special about this. You can choose also the JPL SMAP product in the same way and use the same functionality. And you will look at the time, some of the time series where you can actually, as Dr. Santo was mentioning, where you can actually average the data in a specific area and look at actually and compare the time series from the different data sets. Next. So again, this is the front page of the PO.DAAC, and one of the, obviously the first question is, how do I access LAS? If you go under the dataset access tool, the data access pull down menu, you'll see LAS right there. And LAS is basically a tool that's geared toward what we call level 3 data. That basically means gridded global data sets that you can actually subset. So that we have another tool for the level 2 or orbital data called high tide, but this is a specific example with respect to level 3 gridded data. And again, you pull down the data access under the main page for the PO.DAAC, and you'll see LAS level 3 subsetting. Next. So the first thing, again, what data set do I use? And as Dr. Santos was mentioning, you know, you'll go to the top where you see select data set, choose data set, and there'll be a menu that'll show you quite a few different data sets that we have in LAS. It's not just salinity. We have sea surface temperature, we have altimetry, we have grace, so we have ocean color. So there's a whole bunch of data sets that you can actually access through LAS. But again, for the sake of this example, we're going to focus on two, the remote sensing 70 kilometer and the remote sensing 40 kilometer data set. So the first thing you would do is, again, go under the pull down menu for choose data set and select the data set that you want to work with. Next. So again, this is just an example of the list that you get, when you go under choose data set, and we're going to work again with the SMAP, level 3 surface salinity data set. And you just simply select which data set you want to work with. Next. So again, this is an example. By default, you're going to get a global map of sea surface salinity. And as it's already been mentioned, you see areas of high evaporation, where you see high salinity specifically in the Atlantic, associated with the red colors, and areas of lower salinity associated with the purple and blue colors. And you'll notice that, in fact, just visually, the Pacific and the Atlantic are quite different. So what we want to do now is use LAS to actually subset the region that we want to look at. And this is obviously one of the reasons is that we live on a very dynamic planet. So now we want to actually look at the specific region we're interested in. And for the sake of this example, we're going to look in the Gulf of Mexico and select the Gulf of Mexico. And to do that, you just basically, you'll notice in the left-hand, toolbar, you have the capability to put in the latitude and longitude coordinates. So you would just basically create the box that you want to subset, and then once you created the data set, now you go in and you create the area of interest that you want to work in, and you move forward with the subsetting. Next. So again, you pick a specific area, and in this case, we're going to pick, the Gulf of Mexico. And remember, this is a key point. Every time you change a parameter, whether it be a subsetting, the area that you're subsetting, whether you be, whether you be the functionality, for example, creating a time series plot, as Dr. Santos mentioned, also creating a Hofmuller plot, you have to always click the update plot, which is on the top, of the toolbar. So every time you create something new, you have to click update plot, and that will give you the new plot. Next. So again, this is the Gulf of Mexico, and this is the 40-kilometer product in the Gulf of Mexico. You'll notice also, close to the coast, you'll notice that you have the landmass, but you also notice this white, color indicating no data, a little bit further from the land. And this is also because of issues of satellite and data sets that have a certain level of land contamination. So you'll notice also that, for SMAP, you'll notice there's a certain area beyond the land that you also get land contamination, and you get no retrievable data in that area. And you'll also notice just quickly in the Gulf of Mexico, you'll notice close to the land, you'll notice the purple and blue color associated with lower salinity values. And basically, again, because this is an area in the Gulf of Mexico where you have a lot of river input, a lot of fresh water discharge, including one of the largest rivers in the world, the Mississippi River. And this is just an example, but what we want to do now, this is again using the 4-kilometer SMAP data, and this happens to be for the 31st of March of 2015. Again, nothing inherently special about this date. You can select whatever particular day that you actually want to visualize the data for. Now let's look at because this is a system that has a lot of river discharge, we're going to look at the specific period of time where you have a lot of freshwater discharge into the Gulf of Mexico, and this usually happens during the late summer season in the Gulf of Mexico. So we're going to look at a specific example showing both the 40-kilometer and the 70-kilometer data set. Next. And again, now you change basically you go to the pull-down menu again, and now you have to always click Update Plot, and we're going to now put in different dates. We're now going to look at July to actually look at the time period when you get the most freshwater discharge into the Gulf of Mexico, and you're going to change the date based on the pull-down menu, and now you have to hit Update Plot. Next. So once you've updated the plot, you get a nice new, image of sea surface salinity in the Gulf of Mexico for that particular date. And again, you'll notice the difference. This is the 40-kilometer data set, and you'll notice the difference between the last image and this one. This is in the summer, and you'll notice the, huge, freshwater signal in the northern Gulf of Mexico, again, associated with major riverine discharge into the Gulf. And this is the purple and blue, once again, of freshwater, pressure water associated with these river discharges. And again, this is a highly variable, area, because it's not just because of the river discharge, but because it's a semi-enclosed basin, you have a lot of evaporation also. But additionally, you have the loop current that brings in saltier water, in between the Yucatan and Cuba. So that brings in saltier water into the Gulf of Mexico. You have the loop current, you have eddies. So this is a highly variable system, with respect to salinity. And let's now say, what's the difference between the 40-kilometer and the 70-kilometer data sets? We want to look at that. We have an application, we want to, figure out which data set we want to use. And so we want to look at these differences. And this is a very nice functionality, about LAS that lets you do these kind of things very quickly and visualize the data, very quickly. Next. So now you go and you hit, again, you hit plot options and you click on the different data set. Now you're going to click on the 70-kilometer data set. You have to go back to the left-hand, toolbar, and now you're going to click the 70-kilometer data set. And again, you have to hit update plot. Next. And this, again, shows you, just for the sake of comparison, this shows you the 40-kilometer OSS product, which has been a little bit interpolated to fill in gaps and all of that. Next. And now this is the 70-kilometer product. And you'll notice one of the things you should notice immediately is the 70-kilometer product is smoother. It still has both products show the major features. The 70-kilometer product, though, is definitely smoother than the 40-kilometer product. And this is, in general, the product that you would probably want to use, for most applications. But this gives you also, again, this gives you a really nice tool to be able to compare and whatever. Again, we're focusing on the Gulf of Mexico, but there's nothing inherent in LAS. This is very, very nice. It lets you apply these kind of comparisons to whatever area, you happen to be working in. Next. Again, this is the, you go back and you hit, now let's say you want, now let's say you want to create a time series, just to show you this functionality. And you're going to create a time series from both the 40-kilometer data set and also the 70-kilometer data set. So you have to also put in the, the length of time. You have the choice of the start date and you have the choice of the end date. And again, every time you do this, now you have to go back and update the plot. So we're going to do this and show you an example from both the 40-kilometer data set and the 70-kilometer data set. Next. So again, you have to put in the start date and the end date. Next. And this shows you the time series. This is, again, averaged over the entire Gulf of Mexico. This is an example, from January to December. This is 1 year, from January to December of 2016, and then this happens to be the, the 40-kilometer data set. By the way, the other thing that LAS has is a very nice compare option, which we won't have time to use, but this is a very nice feature also about LAS. So again, every time you do this, you have to hit the update plot. Now we want to start comparing what do these time series look like? Are there any differences between the 70-kilometer and 40-kilometer? Next. So again, this is now the top is the 40-kilometer, again, averaged over the entire Gulf of Mexico, and the bottom is the 70-kilometer salinity averaged over the entire Gulf of Mexico. And one thing you can tell, it's hard to even see a difference. So doing these kind of averages over a large area of the Gulf of Mexico, you don't see a big difference between the 40-kilometer and the 70-kilometer data sets. And you really shouldn't, because where you should see the major differences are on very, very small scales and maybe particularly also along the coast. But over these larger scales where you're averaging over an entire basin, you really don't see much of a difference between the 40-kilometer and the 70-kilometer data sets. Next. And now I just want to show you a quick animation. This is really, I think, amazing, because this shows you one of the advantages of SMAP is the higher resolution. And you'll notice the freshwater discharge from the Amazon plume. But it's incredible as you see this fresh water coming out from the Amazon. It gets captured by the North Brazil current, and then it's vectored north, and then it also gets captured by the equatorial current system, which actually takes it further, into the eastern, Atlantic, tropical Atlantic. But you can actually, you look at the fine scale of this, you can see eddies, and you can see the meandering of the freshwater plume as it's caught by these currents. This is pretty spectacular, and again, the resolution of this is the resolution of SMAP is something that allows you to see these kind of features that we couldn't see before in some of the lower resolution data sets. And of course, you can also see the the freshwater discharge in the Gulf of Mexico. Next. So just recapping quickly, what's the first thing? Obviously you go into LAS, you can log in, you can access it directly from the PO.DAAC site. Then you choose what data set you want to work with. And then once you've chosen the data set, this is really very critical. You always, every time you change the functionality in LAS, you have to hit update plot. So you can also subset. You can basically look at the map on the left hand, toolbar, and you can put in the coordinates for the area that right underneath the map for the area that you want to subset. And you can also select the time range, and selecting the time range allows you to do, spatial averages over the specific time range. Again, having to hit update plot every time. And then also, this is a feature that I really want to stress, we didn't have a chance to look at it specifically, but one of the nice things about LAS is that it lets you save, it's not just a visualization tool. Again, with subsetting and the time series, you can actually save the data. And you can save it in different formats, from NetCDF to ASCII to CSV and to ArcGrid. LAS allows you to save the data, and you can actually work with it and use it on your own favorite, favorite software. And there's other capability that we didn't exactly have the opportunity to look at specifically. There's a correlation viewer too, which allows you to look at correlations between the data, and obviously you can also animate the data and look at the, movies, creating from the time series. Next. So I just want to wrap up, and one of the things to just remember, when we look at the accuracy of salinity and what we're doing with SMAP and Aquarius, we're looking at accuracies of 0.2 practical salinity units, or the analogy of that would be 1/8 of a teaspoon of salt in a gallon of water. So that's pretty amazing when you think of how accurate we're measuring salinity now. Again, 1/8 of a teaspoon of salt in a gallon of water. Thank you very much, and I'll turn it back to Jennifer. Thank you.
Okay, thank you, Jorge. So at this point, what we'll do is we'll transition to a final set of polling questions, and we'll give these questions about 2 to 3 minutes or so, and then from there we'll move directly to the Q&A period. We will extend the Q&A period an additional 10 to 15 minutes due to a little bit of time that was spent with a couple of technical difficulties early on, for those of you who are interested or able to stay on the line. All right, everybody, so thank you. We'll give this 2 to 3 minutes, and then we'll move directly to the Q&A period. All right, everybody, we're going to give this just short of another minute or so, and then we'll move straight to the Q&A section. Okay, everybody, at this point, let's go ahead and transition to the Q&A period. And we do have a couple of questions that were asked a few minutes ago, so we'll start with those. But before we do, really quickly, you'll notice in the after the Q&A pod, there is a pod that contains some useful resources, links to the NASA Earth Data landing page, which provides access to all 12 of NASA's EOS DACs, the Physical Oceanography Data Center, some NASA Salinity-specific resource sites, a link to Dr. Meisner's, the remote sensing systems main page as well, where you can access some of the data products, and also a link to sea surface salinity tutorials. So with that, I would like to start with our first question. The first question is, can we overlay two time series in a single plot? So I leave it to all of you to determine who answers that question.
This is Vardis. I can take that question. So in this particular tool that we were demonstrating, LAS, there isn't an option for actually overlaying two different variables or different data sets on top of one another. However, it does have a feature, and we didn't really talk about it. There is, in the main sort of panel window at the top left, there is a button that says Data Compare. And what that allows you to do is actually bring onto the same screen up to 4 different panels. These panels can hold data for the same data product, the same variable or different variables, for different time periods, different spatial regions. You can have on the screen up to 4 panels synchronously. So while they're not, physically overlaid on one another, they are sort of, you can sit different data layers side by side and easily undertake comparisons. And it's a very interesting and useful feature for visual exploration and analysis of data.
Well, one thing just to add, one of the nice things, again, even though that particular feature or functionality isn't available through LAS, again, you can download the data in ASCII, you can download it in comma delimiter, and you can just put it into your favorite Excel spreadsheet and then do the plotting, and that's very quick. So again, even though you can't do that directly through LAS, you have this a nice capability is that you can actually save the data in these formats, which you can then very easily use to do your own plotting.
Okay, great. Thank you, Jorge, and thank you, Vardis. So now our next question is, can you put with lines in one plot? I'm not sure if that is getting to the same question to a degree.
No.
Yeah, can you repeat the question, because I'm not sure.
So the question is, if this particular user, let's see if he's still online. Not still online, it doesn't look like. So we may need to address this separately offline. Okay, so there was a comment to Jorge's response rather than a question, and one of our scientists actually at PO.DAAC mentioned that you can export the data into plotting applications that allow overlays like Jorge just mentioned. Are there any additional questions? Okay, great. We're glad that that helps. And then the other thing I wanted to mention is that today's presentation files, including the The movies are available for download in the file sharing pod in the lower right-hand corner of your screen. If you highlight a file, you'll be prompted with an option to download those files. The webinar presentation files are separated into two. One of them is labeled with Santos Vasquez, and then the first half of the webinar, where Dr. Meisner was speaking, is labeled with the August 2018 final file, just for some reference. Okay, and so the next question is the finer resolution due to SMAP's bigger antenna as compared to Aquarius data?
Hello? I think I'm probably the one supposed to answer. Can you repeat it? Because I'm having trouble to see the question here.
Yes, and so the question is the finer resolution of SMAP data due to SMAP's bigger antenna when compared to Aquarius data?
Short answer, yes. Yep.
Okay, thank you, Dr. Meisner. If there are additional questions. Anybody have any additional questions? Okay, well, what we'll do is, if there are no further additional questions, we'll leave the virtual meeting space open for 10 minutes or so to give people an opportunity. If you think of something, feel free to jot that down into the Q&A pod. I will be sharing that information with our speakers today, so they can certainly follow up with you offline. And then just a quick plug for our upcoming webinar, which will be actually next week on Thursday rather than a Wednesday, and we will be talking about how to use subsetting tools developed at our Oak Ridge National Laboratory, DAAC, to subset, visualize, discover, and access both MODIS and VIIRS data products with a specificity to land data products. Okay, so thanks to all of you for your patience. You know, we had a couple of really short technical difficulties. That's not the norm, but we worked through it, and I'm very appreciative that all of you were able to attend today. And thanks to all of our speakers for their time in today's presentation. And then you'll be looking for, the next couple of days, a link to the YouTube recording, which we'll place on our YouTube channel, as well as a direct link, which will enable all of you to interact with the useful resources pod, as well as the presentation files pod. Those are two persistent features with a direct link to the recording, and I'll explain that in my follow-up message. So let me take a quick peek to see if there are additional questions at this time. Yes. Okay. Oh, okay. So it doesn't look as though we have any additional questions. However, I know that one of our other data centers will have a data recipe soon on how to create multiple variable plots with a package called plot.ly or plotly. And I will include that link in the follow-up thank you message for all of you. And thanks to all of you. And at this point, what we'll do is we will log off from the audio component and leave the virtual meeting space opened. All right, and I hope to see some of you or all of you at an upcoming webinar. All right, thanks, everybody.
Thank you.
All right, goodbye.
Thank you. Bye.
You're welcome. Thank you.